Hi everyone, so today we're going to be modeling a mass spring system using differential equations. We're told that the mass of the spring is 1/8 kilogram, the damping is 2, and the stiffness of that spring is 16. So a DE with a mass spring system is just a second order differential equation where we have the mass times the second derivative plus 2 first derivative, or sorry, that should be the stiffness plus, the stiffness y, and then this middle term here, this is going to be damping, right, times that first derivative. So a little bit of a rocky start, but I apologize. Basically, our DE will look like this, and my idea is to show you how to graph this and how to find some important information. So we're specifically asked what's the equation. Let's put it in generalized, easier to work with format, and then when will the spring return to the equilibrium position first. So we're gonna first get the overall equation, plot it on Desmos, and then go from there. So let's begin. So initial conditions is that the spring is starting at time 0 at 0.5 to the left, so we'll call the left side the negative x direction, right? So this side is negative x, this is positive x, right? And we're told that it has a leftward velocity, so the spring is traveling in the negative x direction, or the left, so it's going to be negative 4 meters a second. Okay, so that, and the idea is that, okay, the spring at 0.5 out, maybe we kind of yanked on it and it's still continuing to go 4 meters a second in that direction. With this information in mind, we can solve this differential equation. So let's go ahead and do that here. Let's get rid of this. Okay, so to solve this DE, we know for a homogeneous solution, we can set, we can find the roots to this if we look at it as like a polynomial, where this is x squared plus x plus some constant, right? This is just something we could factor or use the quadratic formula to solve. So what we'll do is we'll call this r squared, so 1/8 r squared plus 2r, right? So r is just going to be that first derivative, some variable kind of like x or y or z or something like that, right? And r squared is just that squared, right? That makes sense because this is y prime, this is y double prime. And then y we'll just treat as a constant, so we'll call this 16 equals 0. To make this a little bit easier to either factor or find the roots of, let's multiply everything by 8. So this is going to be r squared plus 16r, and then this would be 128. I think that's right. We'll go with it. And this should be relatively easy to solve. We're just going to use the quadratic, where negative b plus or minus the square root of b squared minus 4ac divided by 2 will give us the roots, and we should get two roots, so r1 and r2, right? I'm going to go ahead and just simplify this. I already did this, and this should be 2a, my apologies, but our constant, that's why we multiplied everything by 2, so this is just 2. So when you plug everything in, where this is a, right, this is a 1, this is b, this is c, you're going to find that the roots to this is going to be equal to negative 8 plus or minus, and I'll go a little bit before. We're going to see it's going to be the square root of negative 256. And you're probably curious, if you've never worked with imaginary numbers, how can I simplify this? And to do that, all you have to do is, so negative 8 plus or minus, factor out the negative 1 square root. So you can write this 256 is equivalent as writing it as -1 times the square root of 256. Remember your radical rules, right? And then this will just simplify to the imaginary number I. So this is going to be I times the square root of 256. And we'll see why we can work with that in just a moment. Hopefully you've already learned this in your course, but for those who haven't, I'll just quickly go over this kind of idea. Right, so a spring can have these imaginary numbers, and usually that's where we hit a roadblock and we say, oh crap, what do we do? But it's not the worst thing in the world. So factor out that I, right? 256, the square root of positive 256 is 16, I think. Let me just double check. But it sounds right. 16 divided by 2, that's going to be 8. So our roots are this, right? -8 plus or minus I, 8. So R is going to be equal to I, or sorry, let's not look at it as like distinct R values. The way that we present the solution in a more simplified way, instead of going through all that work, we're going to say that this is some alpha value and this is some beta value, but in beta we omit the I. So the I is still there in the solution, but using Euler's identity, where E I T equals cosine, I'm forgetting, T plus sine Ti, right? So this is Euler's identity, and we're allowed to use that in our solution, so we're just going to omit the I for now. But let's treat this as an alpha value, and we'll get into what that means in alpha values. So I need to draw here. It's not letting me draw, man. What the heck? There we go. Okay. So we can present a generalized solution as y of t equals, it's going to be E alpha t, right? So that's where our alpha value is going to come in. This is going to be the -8 multiplied by C1 cosine beta t, right? Plus C2 sine beta t. So it gets kind of tricky when you look at this, right? Because it's just going to get to prove that this works, but it comes from Euler's identity, and there's a whole proof for that, which I'm not going to get into. But your general solution for, we call this auxiliary roots or complex roots, is going to be this here. So if we draw out, if we add in all our values now, it's going to be E to the -8t times C1 cosine, and this is going to be 8t. We're going to omit the I kind of alluded to that earlier. The reason that we derived this is so our roots are not complex, right? This solution, if we didn't do this, where we found the E alpha t, C1, C2, it would have complex numbers in it, and we don't really want that. We want whatchamacallit, we want real numbers, not imaginary. You can't imagine, well, you can imagine imaginary numbers, but you can't work with them. So I hope you get the point there. So we're going to call this C2 sine 8t. So this is a general solution depending on what C1 and C2 are. We're going to find that our initial conditions will help us find C1 and C2. But a general spring is going to follow the motion of this graph, right? So if we want to know at any point, we have how the spring is changing, right? It's changing with the second derivative and the first derivative and y. But that's not really helpful to give us a position of that spring at any given time. You could think of this as in a car, right? We want to know where that spring will be after hitting a bump with some initial condition. And that's what these initial conditions in the differential equation will help us to find that idea, where is that spring going to be at some amount of time. And it's going to be dependent on, our inputs to this. T is time, and y is going to be displacement from equilibrium. So we'll see what that looks like after we find C1 and C2. And it might be a little intimidating to find C1 and C2, but all you have to really do for this, and if I just move over, is we're going to use the initial conditions to find this. So for right away, we can find, I believe, C1 if we say that y of 0, if we're looking at just our normal solution, we're going to say if we want to find, I think it would give us C1. If we want to find C1, for example, what we would do is we'd say, okay, 0, because y of 0 is negative 0. Sorry, I made a mistake there. I should rephrase. Y of 0 is equal to negative 0.5. So this solution down here, we're going to set equal to what we have up here. Okay, so that's where that's coming from. And we're going to plug in 0 for every t value, right? Because it's a function of t, and the t value we're evaluating at is 0. Time of 0, the spring is that far over. So e to the negative 8, 0 is going to be 0, and e to the 0 is just 1. So we'll rewrite this as 1, which will just omit. So e to the negative 8t falls out of the equation. Please try and justify that in your head. It's kind of important here. It makes things a lot simpler. So let's move on. C1 cosine of beta t and of 8t. If t is 0, that would be cosine of 0, and we know cosine of 0, right? If you're on the unit circle, you're straight across, that's going to be a cosine of 1, right? Because it's the x. So it's just going to be C1. C2, sine of 0, right? 8t, plug in 0, you're going to get sine of 0, and sine of 0 is 0, so this is going to fall out. So C1 is going to be equal to this here. Okay, so hopefully you were able to find C1, and for C2, you might think to yourself, well, can I plug in negative 0.5 here and reevaluate? Well, that would be a no, right? Because sine here is going to be a big issue. If we plug in sine of 0, C2 just drops out of the equation. So we have to get another equation. And to do that, what we'll do is we'll take the derivative of this and then plug in our first derivative initial condition. So to do that, just take the derivative and be smart about this. Treat this, oh, that's a terrible color to pick. Treat this as, u. Treat this as v. So when you do your product rule, do them together. And it might be a little daunting, like, oh crap, how am I going to solve this? Trust me, it's not bad at all. You just have to do it and see what works. So let's go ahead and do that. So let's take first the derivative of the cosine bit. So e to the negative 8t. C1 cosine, so this would be, oh, I always hate thinking about my sine derivative. I'm so bad at this. I know it's going to be 8, right, because derivative of the inside. C1, derivative of cosine, oh, I think it's negative sine. So we'll put negative 8, negative sine 8t. And then we're going to put, and then sine's derivative is cosine plus 8 C2 sine 8t. So I know it looks messy, right? But that's the first part. And something that you'll notice right away, if we plug in our initial conditions now for this first part, this sine bit, oh, sorry, I made a mistake. C2 cosine of 8t. Okay, my apologies. If we plug in our initial conditions, this negative 8c1 sine 8t, a whole term is going to cancel because sine of 80 or sine of 0 is going to go to 0, and then all that cancels out. But we'll get to that a little later. It will just leave us with the C2 part. And then it's going to be minus 8 e to the negative 8t, right? Because that's the derivative of this e to the negative 8t part. right? And this would be plus the other part of the product rule, right? So negative 8 e to the negative 8t. And then let's just plug in that v is what I called it, right? C1 cosine 8t plus C2 sine 8t. So it gets a little bit easier now. If we were to plug in the 0 here, it would turn out like this. So let's just go through every term. Let's pick green here. So negative 8 to the 0 is going to be 1, so this will cancel, right, if we're evaluating this term here. So negative 4, right, negative 4 equals negative 8 C1 sine 8t evaluated at 0 is going to be 0, so this will cancel, right, because sine of 0 is 0, right? I kind of said that earlier. 8 C2 cosine 8t at 0, right? Cosine of 0 is 1, so this is just going to be 8 C2, right? Negative 8 e to the negative 8t. This will simply just be negative 8, right? Because this will go to 1, right? Leaving us with just this left, right, as a constant. And that's going to be multiplied by whatever this is in here. And if we look at that, C1 8t, that's just going to be C1, right? And then C2, right, this will cancel because, again, for the same reason we had up here. So I know I'm going a little fast, but it's kind of important we get moving here. But now we see we have some equation, right, that it will relate C1 and C2 to some constant. And to find C2, we just need to plug in what C1 actually is, which is negative 0.5. So negative 4 equals 8C2. And if we look at this, negative 0.5, right, times negative 8 is going to be plus 4, right? And C1 is no longer there because we gave it a value. If we subtract that over, negative 8 equals 8C2, so C2 equals negative 1. So hopefully you follow there. It's not the most horrifically hard thing to find. It's just some simple algebra and some calculus too. But hopefully you were able to find that C1, C1 was here and C2 is here. So let's plug that back into our solution. Okay, so let's bring this down here. Y equals e to the negative 8t. C1 was negative 0.5 cosine 8t. And I have to erase a little bit here. I apologize. I should prepare a little better for this, I think, right? You know what, let's just do it like this. Let's go here. Y equals e to the negative 8t. C1 was negative 0.5 cosine of 8t, right? And then we're going to plus C2, which is just negative C2, so negative sine of 8t. So this is going to be a general solution for our differential equation. We have everything plugged in for t. Not a general solution. It's a specific solution, right? Because C1 and C2 are defined. It's a specific solution that tells us exactly how the position of that spring is changing. So what I want to do now, and I hope that you guys can see, although I think I have to change it here. Let's take a look. Desmos graphing calculator. Here we go. So I need to show this, hide that. All right, awesome. So here's going to be Desmos here. We're going to plug in exactly what we had, and hopefully we'll find a solution from that, or we'll see how the spring is changing. So take a look. Y of t, right, because that's going to be our variable. Maybe we have to put in terms of x. I know they're a little iffy on notation, so let's just do y of x, right, because it's x, y. So is going to be equal to e to the negative 8x, right? So we have that little part here. We have negative 0.5 or 0.5 cosine of beta t, and in this case 8x, okay, minus sine of 8x. Okay, so let's look at our solution here in a little bit of a logical sense, and what I want to do is omit everything behind t equals 0, right? Because time can't equal 0 in the real world. You know, maybe in like a very niche field you have t equals negative 2 seconds from blast off, but that's not what we're modeling here, because if you look, the spring isn't going to reach a height, you know, before we pull it back and give it some velocity. It's not going to be at 13.26 meters from equilibrium. That's just not how the spring is behaving. So we see a deviation from the true formula in this crazy behavior, right? I mean, that just goes up really high. So we don't expect the spring to exhibit any behavior that we can accurately predict and is true behind t equals 0. So because of that, let's restrict our domain. X is greater than 0. So, you know, you hit the bump, right? And it has some downwards velocity, right? The slope of this tangent line kind of here in this range here is negative 4 meters a second. It's going to hit the absolute bottom, right? You can think like you're kind of hitting like a pothole, but imagine that pothole. You know, if this is a car, this is kind of like a spring in a car. You're going to hit the pothole at the bottom, right? The car is dipping down this low, right? Of a position of negative 0.573 meters, right? Kind of a lot, right? Half a meter. You know, of course, really dipping down. But then imagine it's not hitting the side that would pop it up, right? It's just the spring counteracting. And we're going to jump all the way up, right, to equilibrium, so kind of flush with the road, right? You could think as x equals 0 as the road, or sorry, not x equals 0, y equals 0 as like the parallel with the road, and then the spring will jump up, right? It's going to overestimate that bump, and it's going to reach a maximum value that we see here, and it's going to come plateau back down, right? The spring kind of, and then it kind of equalizes the car out. So hopefully you can kind of see it, and you know, assuming there's no more potholes, smooth the driving. We will see deviation because what is happening, this is a sine wave. It's going to go kind of up and above the ground, but you know, it's relatively flat, right? You can see it oscillates between positive and negative, but it's very, very small to a unfathomably minute degree. So basically flat there. So we understand the behavior of the graph now. We understand what's happening with this spring, but now we have to find a couple of things. The problem specifically asks us to put it into a easier to work with way, which requires a fee. Not an actual fee. I'm not going to charge you guys for this information, but it wants us to put the solution, and sorry, let me switch back over here. It wants us to put this overall solution in y equals e alpha t sine beta t plus phi. This is just a different way to express it. It comes from the fact that sine of a plus b, and sorry, there should be an a here, an amplitude. Sine of a plus b equals all that junk, right? The double angle identity, I think it's called. It's been so long, but sine of a plus b, I'm gonna just search that up, and we'll bring that up here. Sine of a cosine of b, and then plus cosine of a, sine of b. So we're going to use this identity to kind of work backwards and understand how we can write our solution. I don't usually like to go the other way. It's a little tricky and not intuitive to follow. Sorry, that's how I should put that. So let's rewrite this as so sine. We're just going to work with the sine of a plus b here. Let's call sine of beta t plus phi, right, is going to be equal to sine beta t, and that's going to be cosine of phi plus cosine beta t sine of phi. Okay, so we're going to make a little identity here between phi. Okay, so phi is going to be the relationship between constant c1 and c2, where the hypotenuse is c1 squared plus c2 squared, right? That drawing is just awful, but the square of the two, the Pythagorean identity, basically, right? Tangent is the tangent line, is c1 squared plus c2 squared square root. Okay, basic trigonometry. I really hope that you kind of follow that. But this is going to be our amplitude here. It turns out that is a. So this part here, and we'll see why that's important in a second, but we'll ignore that for now. But we need to identify what cosine of phi is and sine of phi is. So let's do that now. So let's see. C1 in this case we said was negative 0.5, right? This is negative 1. Okay. So let's make an identity here, and let's not even really put values to this yet. Cosine, cosine of phi is equal to, remember that's adjacent, so c2 over the square root of c1 squared plus c2 squared. Sine of phi is going to be the opposite, right? So c1 over, right, opposite over hypotenuse, so that's going to be c1 squared plus c2 squared. Okay, so these are our general identities. We're going to plug this in, and we're going to see why we can get back this solution here. And from doing that, what we'll do is assign it to be this solution. I'm just kind of proving why you can work backwards here. But this is the idea, right? So we have this triangle where the amplitude of all of this sine wave here of e to the at sine beta t, the amplitude of that wave, right? Amplitude factor. It's a really weird A, amplitude. It's not really feasible to look at it as amplitude, but is going to be the hypotenuse of this triangle, C1, C2. Okay, so let me just make sure that this works out here. Cosine of phi, right? C2, yep. All right, I just had to make sure, because if you flip them, you'll get the wrong answer. Although I believe they are interchangeable. But in this case, we want to make it these guys. So we have cosine of phi and sine of phi. So let's just plug that in, right, to the alpha, and expand this out, right, to kind of show that this works, right? So y equals the square root of c1 squared plus c2 squared And then we're going to have that E alpha t, so negative 8t. And then we're going to have C, or sorry, I should say, this is different now. Sine of 8t. And then cosine of phi is C2 over square root C1 squared plus C2 squared, right? Okay, so that's its own entity, right? Multiplied by that sine of 8t. And then it's going to be plus cosine of 8t. And then we have sine of phi, so that's going to be C1 over the square root of C1 squared plus C2 squared, okay, in parentheses. Okay, so now we're going to do a little bit of a simplification. Hopefully you will see the similarities. So what we'll do is we're going to take this bit and simplify these bits inside. So if you notice, they just will cancel out, right? Because top and bottom of a fraction cancels. So what we'll do is we'll multiply this in. So all they're doing, this is like a phase shift, I think it's called. I haven't really taken linear algebra. I think this is maybe a concept in there. You know, this idea of factoring out the hypotenuse of your constants to make it a little bit easier, right, to look at it as this here, right, this general form. I think that's why they do it. So y equals, right, if this cancels, then this cancels, right, e negative 8t sine multiplied by sine 8t, right, C2 is going to be negative 0.5, right? Negative 0.5 minus this, right, because C1 is negative 1. Cosine of 8t. Okay, so we have this overall solution that we had up here, right? So what we can do now is simplify our solution going backwards now, because we got back what we had. Let's just go backwards and go all the way up here, right, to what we had initially, right? So yeah, let's do that. So y equals, notice this will be the square root of our constants. Square root of our constants squared summed together. So let's go ahead and do that. Square root of C1. So 0.5 squared plus 1 squared. Right? And when we do that, our amplitude is going to be square root 5 over 2. And then this is going to be multiplied by everything we had on the inside, right? But simplified to just sine. Well, we actually need the e first. E negative 8t, right? And then sine beta t plus phi, okay? And beta is 8t. But notice this is also plus phi. And we have to now assess what phi really is. So let's look at tangent of phi. So tangent of phi, you could look at as sine over cosine of phi. So sine over cosine of phi. Or you could just look at C1 over C2. So phi is going to be equal to negative 0.5 over negative 1, right? Or, and this, sorry, I made a mistake. This should be arctan, or tan inverse, of negative 0.5 over 0.5 5. Sorry, I'm running out of room here. It's kind of annoying. Over negative 1, right? So this is what phi is equal to. But I want you to notice that both of these are negative, and this is another annoying point that you just have to keep in mind. If we look at the unit circle, right? If the phi is here, right? Phi of 1/2, right, is going to be like kind of like here. This would be our phi, right? Just of 1/2. That's not really the case, right? Because this simplifies, but C1 and C2 are both negative, so cosine of negative needs to be restricted over here, and then specifically down here, right? Because for the constants to be negative, they have to be in the third quadrant. So really, phi is down here. So we have to add pi to this sine function, right? To bring this this one that would be arctan of 1/2 all the way around to be where it should be. It's going to be the same value, but it's going to help us find these things of mins and maxes, right? This idea. So in our solution, we're just going to add pi, right? And I know that's a little bit out of the ordinary, right? But it's going to look like this, right? Beta t plus phi plus pi, and that's all going to be contained within our sine function. So when we look at our overall solution, sorry, this gets real crazy here. This is going to be plus arctan and that was C1 over C2, so of arctan of negative 2, right? Negative 2 plus pi. Okay, so let's go ahead and plot that. I think we should get out the right answer, although I'm not sure about this arctan. I think I may have done something wrong there. But if we did, we will address that and see where we went wrong, right? I'm not perfect. Things happen. So y equals square root of 5 over 2 e to the negative 8x, right? Multiplied by sine of negative 8x plus arctan of negative 2 plus pi. Okay, so it seems like I got the wrong shifting here. I think this has to be negative, right, to match. So when you graph this, you know you'll make an error if it's going the wrong way. And in our case, this has to be negative, right? And I also did something, I think this should be a half, right? So arctan should be a half. Let's see where we went wrong in our math. This should be fun, right? Let's go back here. So let's see. What did I define arctan as? C1 over C2. Is C1 negative 0.5? Yes, it is. Did it work out that way? Oh, no, I have it flipped. Okay. See, I did do this wrong. You need to flip C1 and C2 here, right? And then it flips it here, and then it flips this back around. So remember how I said if you do this wrong, it will flip everything around? That's the case here. These you can change out. So our overall solution should look like this, but it just changes this arctan to arctan of 1/2, right? So arctan of a half should be what we have here. So sorry for the messiness, but that was just a common error I think a lot of people will make, where this is going to be 1/2, right, instead. Arctan of a half. And you'll notice if you look at our graph now, I'm going to hide both of the graphs, and I'm going to bring back the one that we just made, and you'll see it's the exact same, right? If I get rid of pi, it gets flipped back around, so that's why, remember, we need to be in the right quadrant, so we add the pi on, right? It's something annoying you have to think about. And again, let's restrict our domain, so we're just talking about the times in question where there's positive time, right? We don't go back in time, right? We don't time travel that spring, but because it breaks down the ideal conditions of that spring. But anywho, this is the general or the overall solution put in a more simplified form, and the reason that we do this is so we can solve for the third question. So through all that junk just to ask when will the spring return when will the spring return to the equilibrium position? And from the graph we can deduce that it would be this point here, right? It's going to cross the parallel with the road at 0.33473343 of an x value, or time I should say, right? So about here it crosses. So how can we find that algebraically? And that's a good question. And we don't need to, we can bring up a new slide here because it doesn't really require our work from the past. So let's rewrite our solution. So y equals negative square root 5 over 2. And then this is going to be e negative 8t, right? Did I do that right? Yep. And sorry, did I flip? No, I didn't. Sorry, I didn't flip the camera here. Okay, my apologies. And then this will be C1, sine. I'm getting confused on which one we're going to use here. This is sine of negative 8t plus arctan of 1/2, and then this is going to be plus pi, right? So kind of a lot here. We need to ask ourselves, when will the y value equal 0, right? Because that's when the spring will return to the equilibrium. So if this is the equilibrium, let's say the spring goes out this far, right? The max amplitude that we saw at the very bottom of the graph, right? And then it's going to come back, right? And what is the time when we pass through the equilibrium position of that spring? That's the idea, and that's when y is 0. What will time be equal to? So to solve for this, we just need to look at, what factor here is going to make our graph 0, right? And if we look at this term, we need to ask ourselves the question, will this term here ever equal 0? Will this ever equal 0, right? That's a good question to ask, and the answer is no. The e function never approaches 0. If we look at the e function, it will do this, right? If it's negative, it will come up to it will make a horizontal asymptote at y equals 0. Same thing in the other way, right? It will approach the y equals 0, but never touch it, right? For both forms of e. So just an important thing to keep in mind, that these functions never reach 0, right? So we will not even worry about it when we're talking about when will the function become 0, because to be quite fair, it's just a scaling multiple. So we need to find something of this piece that will make sine 0, right? Because sine can be 0, right? If we look at just a general sine function, right? Sine of 0 is 0, so it goes like this, right? The overall sine function, right, is going to oscillate back and forth. So we'll reach max amplitude, but then we cross the 0 right here, right? Y equals 0. So the way that we can find this is we can say, okay, well, to make sine 0, let's set all of the inside chunk of sine equal to some sort of thing that would make it 0. So to do this, we could set negative 8t plus arctan of 1/2 plus pi equal to something that would make this 0, right? Or to make sine of 0, I should say. Sine equal to 0. And we could look at a few possible values, right? Hopefully this will become a little bit intuitive. We could look at 0, because if we set sine of 0, if we evaluate sine at 0, it's going to be 0, right? We could look at pi, right? Because if we go all the way around the unit circle, just the first two quadrants, that would be 0. We could also look at 2 pi. But notice when we evaluate at these different values, our time, right, our time variable is either going to be positive or negative. So when we look at these possible values of pi n, right, these are multiples of pi n, where n is some whole number value, 1, 2, 3, 4, 5, negative, you could even go. You could look at negative pi if you wanted to, but we won't. We need to find the first one that makes it positive, and the reason, I'll go back to our graph here. If we look at our overall graph, right, and I'm actually going to just get rid of the domain, we're going to bring this whole function, we're going to copy it, we're going to paste it, right? Notice in the negative time direction, remember we're omitting the negative time direction because it doesn't make much sense. Notice it's also passing through 0, and if we evaluate that sign at a wrong point, it might give us in the negative time direction, because that is possible, right? If we evaluate that the inside of sine at 0, pi, 2 pi, 3 pi, you know, and it gives a negative time value, well, we're not referring to this section, we're referring to the negative time section. Remember, that's not the ideal point of the spring. We're asking, you know, on this side, right? So positive t. So hopefully you follow here. I'll evaluate these at all of our time values, but hopefully you get the point. So let's just evaluate at, I know 0 won't be it, right, because we're subtracting over. If we set negative 8t plus arctan plus pi, right, equal to pi, or sorry, 0, it's just going to be negative, right, because negative, right, and then that would also be negative. So that's not good. So let's look at pi. If we did negative 8t plus arctan. Oh, sorry, this shouldn't be negative here. This sine bit, that shouldn't be negative because beta was 8, not negative 8. So my apologies. Let me go ahead and scribble that out. So the negative 8 does not, it's not negative 8. I'm making so many mistakes this video, but kind of have to do it in one take. It's not negative 8, it's 8t plus arctan 1/2 plus pi. So we're going to set all that, because I was confused. I'm like, oh, you would get a positive t. But my apologies, it should be 8t plus arctan plus pi. Now you should be able to see, if we set this, all of this equal to 0, we'd obviously get a negative number, because we'd minus over pi minus over arctan divide by 8. That would obviously be a negative number. Same with pi, right? Because pi minus pi is going to be 0, minus arctan, that's going to be in the negatives, divided by 8, still negative. So we're going to look at 2 pi, and you can go through all these and prove that you'll get a negative time, but we're going to stick with 2 pi here. So 8t plus arctan of 1/2 plus pi equals 2 pi. And all we're doing here is saying, okay, what t value can I set t to make sine evaluate at 2 pi, right? What t value will do that, and thus make sine 0, right? And thus give us a root to our overall solution. So let's just do the math here. We're going to subtract over pi, so this will be pi minus arctan, right? So 8t equals pi minus arctan of 1/2, right? And then we're going to divide by 8. Hopefully that makes sense, right? over 8. So whatever this evaluates to, and we'll just give a rough estimate, right? So let me just calculate that quick. So pi minus arctan of a half divided by 8, that is going to be 0.335 roughly, right? So I'll add the roughly symbol, right? So roughly that amount of time has passed, and we'll see on the graph that that's true, but let's give a rationale. So at this time of 0.335 seconds, so just a split second after we kind of, if we think about this as a car hitting a pothole, at that time we've hit the pothole and we've bounced out of it, right? Or the spring has crossed the equilibrium position at 0.335 seconds, right? Kind of quick, right? That's a good spring. So we're gonna just shoot right back up to parallel with the road if we think about it as a spring in a car. And it's going to be the first real root. If we evaluated this at pi or 0, we'd get a negative time, and therefore we wouldn't really take that into consideration. We could also look at 3 pi. 3 pi would... Oh man, I didn't show my math. Huh. Oops. I'm going to cut this here, I think, but my apologies. I should have shown this part here. This bit will simplify, right? I have to re-explain all that. So just to recap, 8t plus arctan half plus pi equals one of these values that I said, right? We're going to select 2 pi. So 8t plus arctan 1 half plus pi equals 2 pi. Solve, you get a real t value. If we evaluate it at pi or 0, you get a negative number. So hopefully that makes sense. But what this means for our graph, right? If we look at our graph, when we look at our graph, notice, and if we zoom in, right, to what that value is equal to, we're going to see 0.335 roughly, right? So that's a good indication that we got the right answer, right? It's the first real root. If we evaluated at 3 pi, we would get this value here, the second root, and then maybe this root here if we went to 4 pi. So you can do that if you want, but it's not necessary. It's just important to kind of see, just the first one is like, when will we return roughly to the surface of that spring? So that's the idea here. So sorry about me not showing the work there initially, but here it is, right? That's the first root. That makes, this time makes sine evaluate at 2 pi, and then thus 0, bringing us a root, right? Bringing all of this to 0, y equals 0. So hopefully that was helpful. If you did enjoy this video, please drop a like, comment, and subscribe. I would greatly appreciate it, and I hope that you have a wonderful day. Bye-bye.